Please give a round of applause to our next speakers. And enjoy your talk on effective building blocks for securing multi-tenant Kubernetes clusters.
Thank you. Good evening, everyone.
Yeah. Just a quick note for everyone. We have a Q&A online, so if you want to ask questions for the speakers, please go on BSidesSF.org/Q&A, and then we'll read out most of the questions whenever we have time at the end of the session. Thank you.
Cool. Thank you. Good evening, everyone. And thanks for joining us. I know this is last session just before drinks, but the topic is important. It's about platform security, and I believe it's a foundational thing for any application. So it's going to be interesting. Today we are going to share our journey and learnings of securing multi-tenant KTS clusters. What happened?
The slides.
Is it going?
It's not just the GPU as is, it's the theater's projector being weird.
Okay, there we go.
Okay, we are back. I'm Shrikant. I'm engineering manager for infrastructure security team at Snap. I work on securing service mesh platform, which is based on Kubernetes. We use AWS and Google Cloud public clouds for our cloud native infrastructure.
Hey everyone, super excited to be here today. I'm Sagiv Sheelo. I'm a security engineer working on infrastructure security at Snap with a focus on our cloud and Kubernetes security controls.
So we'll briefly talk through the evolution of our platform over time. Then we'll cover why certain decisions led us to consider multi-tenancy. Then we'll talk about how new design change our existing security boundary and introduce new security risk. Next, we'll talk about security controls we built to mitigate against those risks. And as we all know, every project goes through challenges. So did ours. We'll share some of the organizational as well as technical challenges that we faced. So here is a quick history of how our platform evolved until we started this project that we're going to talk about. Snap started on Google App Engine. It was a great platform to bootstrap an idea and scale quickly to millions of users, sending and receiving snaps. However, about 5 years into its life, Snap grew with multiple user-facing products as well as backend services. And as you all know, monolith architectures have limitations. We started hitting those limitations like scalability, developer velocity. At the same time, Snap made a strategic decision of going multi-cloud. Hence, we wanted to have a platform which will suffice or basically support both multiple clouds. And that's why we decided to have an abstraction like Kubernetes that can work on multiple clouds. And that's how we came up with our first service mesh platform. So this is a quick overview of our single tenant service mesh platform. We use open source Envoy for our API gateway at the edge, as well as on the sidecars that on each of the service deployments. Switchboard is our in-house service configuration portal that syncs all the control plane artifacts like service-to-service auth, gateway routes, and other configurations like transport parameters. Each of the services gets its own Kubernetes cluster, which is managed by respective service teams. And this is the bigger difference from what was the existing case and from where we moved on. So every service having its own cluster. So here are some of the design choices for the mesh and the limitations. We chose a cluster per service. We made this design choice to limit the blast radius. And as a cautious step, as we were adopting Kubernetes for the first time that time and at a very large scale. And given our business is of multi-cloud, there was no feature parity between both the cloud providers that we're using and we're planning to use managed Kubernetes service. So we had to make some of the trade-offs there. However, as the number of services grew, it exploded the number of clusters that we had to manage and secure. Our operations were decentralized during that time, and we did not follow any SRE model So we had to rely for cluster management on our engineering teams. And this often delayed cluster upgrades and patching. Our path to production story was not strong. We were not able to enforce golden path CI/CD. This made service rollout to our mesh challenging. It was error prone and needed redundant engineering work. So all of these challenges basically made us to rethink our mesh platform. And as we were rethinking the mesh, we also thought to think about what additional security controls that we need to put into this platform. We had pretty broad IAM for our services. Operators had unrestricted access to the production, and we wanted to minimize that as a security best practice. The deployments lacked provenance, and our production lacked integrity against unknown compromises. Also, as I said earlier, because of the large fleet and exploded number of clusters, the vulnerability responses was a little bit difficult. It was delayed, and it was difficult to get a unified tooling around it. Our fleet had become very heterogeneous, and it was becoming expensive for our detection and response teams or our runtime monitoring tooling to be deployed across such a large fleet. So, given these limitations that we discussed about single tenant service mesh, we thought about optimizing this, and that's how we came up with building a multi-tenancy within our Kubernetes clusters. Now, before we move ahead, let's establish some common terms and understanding of what we mean by multi-tenancy. By single tenant, as I said before, we mean cluster per service. For multi-tenancy, we are packing multiple services within the same Kubernetes cluster. That means the same service would be sharing a node. And though all of these services belong to Snap, they are owned by different teams. Those services might have different profiles, threat models, permission models. These services might be owned by teams which are geographically distributed. So there were a lot of security concerns when running these services into the shared environment. And I think some of you might have similar kind of model, but the tenants could be your customers or some of the third-party code or applications that you're running. But I think the controls or the risk remain similar. So what was the problem statement for us? To build a multi-tenant platform that works on multiple public clouds. And the primary objective is constructing an abstraction that provisions all the Kubernetes primitives for the multi-tenancy and standardize the developer experience across multiple clouds. Basically, we use Google and AWS. And these were some of the tenets that we put ourselves forth. To make an opinionated platform that enforces best practices of CI/CD, observability, and security. So we didn't want it to have a lot of drift within our platform, a lot of heterogeneity because of the way the security tooling, upgrading, patching, and maintenance becomes tricky. And to centralize the infrastructure to enable high velocity of infrastructure changes. So given this problem statement, objectives, and tenets, this is how we started building this. Now I will hand it over to Sagiv, who will take us through deep dives on security risk and mitigating controls in our multi-tenant mesh.
Thank you, Shrikant, for introducing our path to get to multi-tenant clusters. Now we'll continue the discussion on the security risks and controls in multi-tenant Kubernetes clusters. Let's begin by exploring the security risks in shared compute environments. In a traditional single-tenant cluster, the boundaries of a service are well-defined. Only a single service is deployed per cluster, and there is no risk via compute or Kubernetes abstractions for services to interact with each other. However, Kubernetes was not originally built for secure multi-tenancy. When services are deployed to the same clusters, this lack of default isolation can lead to privilege escalation between tenants. For example, permissions via the control plane are not restricted to a single tenant namespace, and pods can be configured to access the nodes, allowing service owners or deployments to abuse the lack of isolation and escalate their privileges onto the node and other services running there. Another risk is the use of overly permissive identities. By default, Kubernetes uses a node identity for all services, and all tenant-required permissions would be needed to give in on the node. It does not follow the least privilege principle. Services would share each other's permissions to cloud resources. Unauthorized access is a significant risk in multi-tenant Kubernetes clusters. Developers often have broad access to their clusters by default. For example, developers may inadvertently or maliciously access other services or their logs belonging to other tenants. Allowing developers access to services owned by other tenants increases the risk of intentional or accidental changes that can impact the entire cluster. So to address all these risks, we need robust security controls. We'll overview each of these controls for the 3 areas. So for privilege escalation, we proactively block known bad configurations that could lead to privilege escalation. We enforce policies for service placement to ensure that services are scheduled on clusters based on their sensitivity and potential impact. And we monitor and patch disclosed vulnerabilities to minimize the risk of exploitation. For the overly permissive identities issue, we implement per service and component identities, ensuring that each service has only the permission it needs to operate, following the principle of least privilege. For unauthorized access, we limit developers' access to only their service namespaces. And we also restrict access to service logs, ensuring that each tenant has access to only their logs. Okay, Kubernetes by design does not provide any isolation guarantees between pods running on the same node. With a simple pod configuration, pods can access the node and all the containers running there. This means that a compromised service pod could potentially access and manipulate other pods on the same node, even if they belong to a different service in a different namespace. To mitigate this risk, we employ a custom admission controller. For those that are not familiar, an admission controller is a Kubernetes mechanism that intercepts and validates requests to the Kubernetes API before they are persisted into the cluster. It allows us, as a production security team, to enforce security controls that apply to all Kubernetes deployments and to block deployments that don't meet our policies. In our case, we built policies into our admission controller based mostly on Kubernetes pod security standards. These are standards for best practices to harden pods in Kubernetes. We chose controls from these standards that prevent known privilege escalation paths that we care about in multi-tenant clusters. For example, we restrict the usage of privileged containers, which have access to all Linux capabilities, and we prevent pods from using the host namespace, which would allow the pods to access the node and all the containers running there. Both of these would break isolation between co-tenant services. And by enforcing rules from these standards, we can significantly reduce the risk of privilege escalation between services in our multi-tenant clusters. We occasionally encountered scenarios where service owners were used to quickly debugging their service by execing into their containers using podexec. You'll recognize that podexec can be extremely risky, especially if there are containers with elevated permissions within a service namespace. To mitigate this risk, we implemented a targeted approach that allows the necessary access while maintaining security. Specifically, we limit the podexec permission exclusively to non-privileged service-owned containers, in addition to auditing all actions performed on production. This control ensures that any privileged system containers don't become a path to privilege escalation. Identities are a basic security concern. The use of overly permissive identities is a huge risk. As you may have run into, pods run with the node identity. In GCP, this defaults to the compute engine service account with editor permissions. Using this identity does not meet least privilege, and especially when we start needing to grant permission for different services to access their data. To ensure least privilege identities, we use workload identity federation to deploy pods with a cloud identity, distinct from node identity. It allows us to deploy pods with per service identities, ensuring each service runs with only the permission it needs. For instance, a friends service might have permission to access the friends database, but other services running alongside it will not be given that permission. We've also ensured provisioning of identities per Kubernetes components and internal infrastructure add-ons. And with workload identity federation, the identity access moved away from the node and onto identities that are linked to pod service accounts associated with cloud identities. Okay, now that we have established our identity model, let's jump into how we think about access. As Shrikant mentioned, when we were reevaluating the security posture of Mesh, One thing we wanted to address was broad developer access to their clusters and deployments. In our multi-tenant environments, hardening access becomes a critical control. Developers with direct access to shared clusters would be a risk to all services deployed. Our platform wouldn't be possible without limiting access to clusters. In order to accomplish this, we limit deployments and changes to the cluster via a golden CI/CD path. The golden path ensures that all changes are tracked and audited and provide a clear trail of who did what and when. And we use RBAC to ensure that service owners' access to their clusters are limited to non-mutating actions in their own namespaces. We don't want to let them do out-of-band changes to production outside of the golden CI/CD path. Now that we have covered access to the deployments, let's cover access to the Kubernetes control planes. They're on the internet by default, and we need to protect against external attacks and follow best practices of limiting access to control planes. At Snap, we have our own Beyond Corp zero trust access pattern, and we use an auth proxy that we built at the edge to provide context-aware secure access. We have added support to Kubernetes to that same proxy, and we enforce its usage by limiting control plane access to its APIs, to its IPs. The security control is transparent to developers. Their experience in connecting via kubectl is unchanged. We generate kubectl context for them that go through our auth proxies and also set their service namespace access by default. So far, we have discussed controls to production. Let's talk about hardening the path to production. To ensure deployments come from our golden path, our CI/CD pipeline signs digests of built images, and our admission controller validates the signatures of pod container images. It allows us to ensure provenance from code commit to the build to the image, and only approved and verified code is allowed to be deployed on clusters, reducing the risk of malicious code being deployed. One of our challenges here was moving away from using mutable image tags to image digests. It required us to update all our platform components to support container image digests. But this cost trade-off was worth the security guarantees that come with using immutable digests that are signed. It's not only about platform security, we also care about the isolation of our service logs. Our services use Stackdriver logging that emits logs to shared cluster GCP projects without per-tenant isolation. To address this, we configure GCP log sinks and buckets that route logs to service-owned projects, ensuring a per-service isolation. It means that each service logs are ingested directly to their respective service-owned projects, preventing unauthorized access to logs from other service owners. And the configurations of these log sinks and buckets all happen automatically during service onboarding to a shared cluster. At this point, all our security controls give us isolation between services and secure the access to them. But for our team and the other security stakeholders, multi-tenancy still felt like a pretty big risk. And in order to further reduce fears around the shift in the security boundary, we had to go back to the drawing board to think of how we want to co-locate services on clusters by threat modeling their attributes such as access to sensitive data, internet exposure, and service tier. It was a tough discussion as it was hard to align on the security benefit given the increase in complexity of managing more clusters. But in the end, to further control the blast radius of services sharing the same cluster, we evaluate a co-tenancy policy at workload onboarding that limits which services can be deployed to which clusters based on their attributes. At this point, we felt our multi-tenant clusters are secure with all the controls and policies, but new kernel vulnerabilities could undermine our assumptions around container isolations, allow a service to escape its boundary and onto the node and other services running there. In order to mitigate against this and other potential vulnerabilities, we enforce the usage of auto-upgrading node pools when possible, and we have the ability to upgrade the entire fleet at any given moment. We have a pipeline for our on-call to get alerted of security bulletins as they're disclosed, ensuring that we patch critical vulnerabilities promptly. I hope this was an insightful journey through all our multi-tenant security controls. I'll now hand off to Shrikant for a recap and conclusion.
Thank you, Sagiv, for discussing all the effective controls to mitigate security risk. So this is a high-level view of our end-to-end platform, and this encapsulates most of the things that we said in this session so far. So if we follow from the left-hand side, notice the engineers, they access the platform only through our zero trust authenticating proxy. And this is our first security control in this entire platform. This validates engineers' identity and access levels. This also has edge policies that enforce things like device trust if in case of sensitive applications. Our engineers only have limited read-only access on the production for their specific Kubernetes namespaces and to just check their deployments. But for mutating operations or changes to your deployments or the service, it has to go through CI/CD. And before each of these deployment reaches the production, it has to pass through a set of security policies. And these security policies are enforced by our admission controller. And if any of these policies fail, the deployment is failed and it doesn't go to the production. So some of the policies are like the controls that we discussed earlier. It's about, for example, doing bill attestation, that is provenance measures indicating that the services have been built through our trusted CI/CD platform. Another policy that we enforce is hardening configurations on our containers. So for example, if there is an unapproved capsys admin capability on the containers, we validate that and then fail those deployments if that's overly permissive capability is not approved. We also validate for the register of the image and ensure that images are pulled only from our approved sources. Now, if you look into the production platform on the right hand or the central right side, you will see there are several platform security controls here. Though the services are running in a shared clusters, there is isolation. For example, each service runs with its own identity, and this is different from the node identity. So the service identity has only permissions that are needed for its own purpose, and every service has specific service scope permissions on those identities. And the node, generally, node identities are permissive in the Kubernetes environments, and we wanted to kind of remove or reduce that attack surface as well. So these run only with permission that are needed for the normal operation of the Kubernetes cluster. So coming to our platform evaluation roadmap. So we went from a monolith to a single tenant service mesh, and now we have multi-tenant service mesh with strong service isolations and workload hardening in shared environments running on our Kubernetes fleet. So this is the most interesting point, and some of the takeaways for you all if you plan to have such kind of initiative in your company. As you all know, large projects are not completed without challenges, and we had quite a few along these lines. First thing is about migrations. I think everyone over here will agree migrations are tricky. There will always be some unknowns in the path, and something will break. For our migration path, we kind of categorize our services into 4 archetypes. We are having services running in legacy infrastructure, services which are integrated as part of merger and acquisitions, services running in our legacy mesh, and the new services which were moving to the multi-tenant environment. To approach this, we basically followed our service tiering model that we have. So the tiering model is based on the business needs of the service and how critical it is to the business of our company. So for example, -1 tier is a foundational service, which basically could be something like API gateway. Tier 0 or tier 1 services are user-facing services supporting core products, and those are directly in critical path. And tier 2 plus services are not in the critical path, but they provide auxiliary functions. So we started adopting the platform with tier 2 plus services. And that's how the initial onboarding started. But what we realized is if we have to ask the tier 0 services to move to this platform, we were not trusted enough, and our platform was not trusted enough. So to go around this, we had to do our own dog fooding, and we had our own tier 0, tier 1 services migrated to this platform. That way we could build the trust amongst our other service teams and product teams, and then we can convince them that this is a platform with strong isolations. We were also recommending change in the developer behavior, and where the direct access to the production, the mutating permissions from the production were removed. And this was a behavioral change for developers. But to ensure that we understand their concern as well, we provided easy paths and alternate paths, as well as break glass scenarios wherever there was a critical business need. This was a large initiative, and the MVPs of such large initiatives go longer. And what we realized is it's very important for leadership to always show patience and kind of endorse or back such project, because the realized impact could take a while. And some of the technical challenges. The requirements of the services were not as uniform as we thought. There were like a lot of bespoke requirements as we started onboarding or started understanding the profiles of the services. Some of the services needed local VPCs. Now this becomes tricky in case of shared environments. Then you have to rely on either network policies of the Kubernetes, but then again, that kind of has to sync well with the either security groups on AWS or the firewall rules on GCP, and the whole model was becoming too complex. We also had to ensure that all this, we provide backward compatibility as we are migrating the services. So we had to cover a lot of different areas to ensure a successful migration. Access patterns are also very tricky. There are operators accessing, then there is network-based access for the services, then we have to have access to the control plane of the Kubernetes, for example, the authenticating proxy that I mentioned. So if we had to move all of our Kubernetes fleet behind the authenticating proxy, that kind of overloads the authenticating proxy, especially if a CD system is going through that. So we had to make some of the trade-offs there to ensure we provide security, but as well as reliability of our infrastructure is intact. And integration of all these controls, these are a lot of moving parts into a platform. That is another trickiness. And there's quite of subtle differences between AWS and GCP. Even if we are talking about abstraction like Kubernetes, once we get into the nitty-gritties of networking and other things, it becomes pretty tricky. So we had to consider a lot of that, and it increased the engineering cost. So this is the final slide. Then coming back to our evolution of the platform, as I said, we started with monolith, then moved to service mesh, which provide security guarantees, productivity gains, cost optimizations, but that was not enough. That's where basically we moved to a multi-tenant Kubernetes platform, which was much more optimized infrastructure, more abstracted out from our service teams. Lot of provisioning, auto provisioning controls and auto upgrades and auto updates on the fleet. But we are not done here. I think there is some room for more iterations, and we started thinking and brainstorming the idea of managed service, which is the idea about to decouple service deployments, whether at the code level or packaging level, so that the engineering product teams only focus on writing code, merging to their branch and interacting through CI/CD, and looking into their deployments only through metrics and charts, while the platform takes care of all the auto patching, auto upgrades, even on the code dependencies or the container image dependencies, etc. So this will be a huge win for software supply chain security as well. So that concludes our talk. We have a couple of minutes for question and answers, but thank you for giving your time, hanging out with us this evening. It was a pleasure sharing our journey with you all.
Thank you so much for our speakers. I think we have probably time only for one quick question. So I can read that out loud if you want. So it's a question from Victor. How does Snap craft Kubernetes configs for team members, especially for those who require access to multiple namespaces and clusters?
So we have an internal tool that lets people connect to their clusters or their services. So they'll request to create a kubectl context for it, and they'll give their service name, and then if there's a few different clusters it's deployed to, then it will let them choose which cluster it is. And then that will set the kubectl config. And that's where we inject the proc to go through the proxy and also to set the default namespace access.
Okay, thank you. I think we don't have much time left because we have to be out by the theaters at 6. So just a couple of quick announcements. You can already enjoy happy hour at the bar that started 15 minutes ago. And in 1 hour, you have a party that's sponsored by Adobe that you can all enjoy as well. Thank you so much, and give please a round of applause to our speakers.
Thank you.